Now we're going to look at some properties of logarithms that make them useful. Here we've got a list of the three heavy-hitting properties. In each of these examples, u and w both represent positive real numbers so that we don't have to worry about domain restrictions. The first rule says that the log base a of u times w can be rewritten as log base a of u plus log base a of w. Or reading it from right to left, it says if you take the sum of two logarithms with the same base, you can consolidate that into a single logarithm by multiplying the inputs. We're not going to go through the formal proofs of these. You can find those in a textbook. But I will try to appeal to your intuition by reminding you that logarithms are the inverses of exponential functions, and we have a similar rule for exponentials. Remember that if you take a to the m times a to the n, that's a to the m plus n. Here we're multiplying two exponentials, and we consolidate it into a single exponential by adding the exponents. We're kind of doing the opposite here. We're adding two logarithms and consolidating them by multiplying the inputs. That's certainly not a proof that this rule is true, but I at least hope it makes it believable. And again, if you care about the proof, you could find it in any good college algebra textbook. The second rule in our list says log base a of u over w is log base a of u minus log base a of w. Again, we have a related exponential rule. We know that if we divide two exponential expressions with the same base, we can rewrite that as a single exponential expression if we subtract the exponents. Here we're subtracting two logarithms with the same base and consolidating by dividing the inputs. Again, kind of the reverse procedure because these are inverse functions. The last rule is quite useful and one of the reasons why logarithms were invented. Log base a of u to the c power is equal to c times log base a of u. This one might be kind of surprising. If you take the logarithm of an exponential expression, you can actually drag the exponent out of the logarithm. Now here I'm going to give you a little bit more of an explanation for why this is true. This isn't a full proof because this really only works for positive integers and it's not very formal, but I just want to give you an idea. I'm going to consider the sum log base a of u plus log base a of u plus, and I'm going to continue adding log base a of u until I've got c copies of it, c terms here. Well, in one sense, we're just adding c copies of the same thing together, so that's c copies of log base a of u. Now I'm going to think of this sum another way. We just said that when you add two logarithms with the same base, you can consolidate by multiplying the inputs. Well, here I'm adding c copies of log base a of u, so I would multiply all of those u's together, and I'd have u to the c power, because there are c copies of u. Well, this sum is equal to log base a of u to the c, and it's also equal to c times log base a of u, so those two expressions must be equal to each other. Now again, that's not a formal argument, and it really only works for values of c that are positive integers, but you can prove this is true for any value of c. So let's look back at our properties and review one last time. Log base a of u times w is log base a of u plus log base a of w. Log base a of u divided by w is log base a of u minus log base a of w. And log base a of u to the c is c times log base a of u. What we're going to do is go through some exercises where we expand expressions and consolidate expressions just to get practice with these formulas. In future lessons, we might use these as part of a larger problem, maybe to solve an equation or something like that. But in most of the examples in this video, we're really just going to focus on using the properties, even if the goal doesn't seem very important. So for example, let's expand log base 3 of x squared y over z to the fourth. We're going to rewrite this using these properties. When you do this, you want to reverse the order of operations. So the last thing you would do in the order of operations inside the parentheses is divide. So that's the first thing I'm going to unravel. How do we rewrite a division step? The second rule says that you can rewrite that as the difference of two logarithms. It's the difference of the logarithm of the numerator and the logarithm of the denominator. So I would start by rewriting this as log base 3 of x squared y minus log base 3 of z to the fourth. Focusing on the first logarithm, I still have multiplication in there. We know we can rewrite that as a sum. Log base a of the product of two factors can be rewritten as the logarithm of the first factor plus the logarithm of the second factor. So I can expand this to log base 3 of x squared plus log base 3 of y minus log base 3 of z to the fourth. And while this is expanded, we actually can perform one more step. We can bring each of these exponents down by the last rule. The last rule says if you have the logarithm of an exponential expression, you can rewrite that as the exponent times the logarithm of the base. So for example, in the first term, I can rewrite this as 2 times log base 3 of x. There's really nothing to do in the second term. And in the last term, we can bring the 4 down and write this as minus 4 times log base 3 of z. Let's try another example. This says expand log base 7 of 49x and simplify. Well, 49x has implied multiplication right here. So log base 7 of 49x is log base 7 of 49 plus log base 7 of x. That's our first rule in action, rewriting the logarithm of a product as the sum of two logarithms. Now here's where the simplifying comes in. Log base 7 of 49 is just a number. See if you can remember how to come up with that. Remember that log base 7 of 49 just means what power do I have to put on 7 in order to get 49? It's the exponent you need on the base in order to get the input. Well, that exponent would be 2. So this is 2 plus log base 7 of x. And here we're not doing anything with this simplified version, but you see why we might want to do that. We've now rewritten this expression in maybe a simpler form. It might be easier to work with. You future calculus students are going to use these properties of logarithms to rewrite complicated functions for calculus purposes. Here's an example of a function where you might do that. We're going to expand the natural log of the square root of x minus 3 times x plus 4 to the 6th power. There's implied multiplication right here. See if you can use that to rewrite this as a sum. So we would start by rewriting this as the natural log of the square root of x minus 3 plus the natural log of x plus 4 to the 6th power. And while that is technically expanded in calculus, we'd want to take this one step further. We'd want to rewrite this without any exponents. And maybe you don't see an exponent in the first term, but we can rewrite this in terms of an exponent. What exponent represents a principal square root? Yeah, 1/2 power. So we're going to rewrite that as x minus 3 to the 1/2. And now we can bring those powers down by that last rule. Log base a of an exponential expression can be rewritten as the exponent times the logarithm of the base. So we can rewrite the first term as 1/2 of the natural log of the binomial x minus 3. And we can rewrite the second term as 6 times the natural log of x plus 4. Okay, let's try going from expanding expressions to consolidating expressions. And we're mostly going to use this technique to solve equations, but in this video we're not ready for that. Here's an example where the consolidation is kind of useful though. This says write log base 2 of 72 minus log base 2 of 9 as a single logarithm and evaluate the result. Now I don't know what log base 2 of 72 is. That's asking 2 to what power is 72? I can estimate it, I guess. It's got to be somewhere between 6 and 7. But I don't know exactly what it is. Same with log base 2 of 9. Log base 2 of 9 is going to be a little bit bigger than 3 because 2 cubed is 8. But I don't know exactly what that is either. I can tell you what their difference is though by consolidating them. Log base 2 of 72 minus log base 2 of 9 can be rewritten as a single logarithm using that second rule. Read it from right to left. It says if you take the difference of two logarithms with the same base, you can consolidate that into a single logarithm by dividing the inputs. So I can rewrite this as log base 2 of 72 over 9. And of course 72 over 9 simplifies. It simplifies to 8. So this is just log base 2 of 8. Log base 2 of 8 is the exponent you have to put on 2 in order to get 8, and we know that's 3. So while I can't tell you what log base 2 of 72 is, and I can't tell you what log base 2 of 9 is, I can tell you that when you subtract those two numbers, you get 3. So there's an example of the consolidation rule for subtraction, and you can see it was marginally useful. We were able to take an expression that looked kind of complicated and simplify it down to an integer. This next example is just practice for practice sake. Write 5 times the common log of p plus 3 times the common log of q minus 1/3 times the common log of r as a single logarithm. I see that these first two terms are added, and your instinct might be to multiply the inputs, but I want to show you something about the rule. Notice that in our rule for consolidation, there are no coefficients in front of the logarithms. Well, there are, but they're implied ones. There's certainly not a 5 and a 3 like you see here. So we've got to get those coefficients out of the way, and this is where the third rule comes to save the day. Read this from right to left. It says if you have a coefficient on your logarithm, you can drag it in as the exponent on the input to the logarithm. So we're actually going to do this on all three terms in anticipation of doing the subtraction step as well. I've recopied the problem here to make it a little bit easier to see what we're doing. I can drag in the first coefficient as an exponent on p, so this becomes the common log of p to the fifth. I can bring the 3 in as an exponent on the base q, so I get the common log of q cubed. And then I can bring the 1/3 in as an exponent on r, and I get minus the common log of r to the 1/3. I'm going to consolidate these from left to right. If you think you can do this all at once, I'd encourage you to try that. But I'm just going to focus on these two terms to begin. We said that when we add two logarithms with the same base, you can consolidate them into a single logarithm by multiplying the inputs. So when I add these two logarithms together, I get the common log of p to the fifth times q cubed, and then we're subtracting the common log of r to the 1/3. Now we have one more consolidation to do. When we subtract two logarithms with the same base, we can consolidate them into a single logarithm by dividing the inputs. And so we can write this as the common log of p to the fifth q cubed divided by, I would leave it as r to the 1/3. A good substitution for that would be the cube root of r, means the same thing. Which you choose here doesn't matter because we're not doing anything with it, this is just practice. You would make that determination based on what you're doing with the logarithm. So for algebra purposes, it might be nice to have the radical down there. Rewrite it as the cube root of r. For calculus purposes, we'd probably want to leave it as an exponential expression. Here's one I want you to try. This says write 7 natural log of x minus 2 minus 3 times the natural log of x minus the natural log of x plus 10 as a single logarithm. Pause the video and give that a shot. Hopefully you remember to drag those coefficients in as exponents first. This is the natural log of x minus 2 to the 7th minus the natural log of x cubed minus the natural log of x plus 10. When we subtract those first two terms, the x minus 2 to the 7th will be in the numerator and the x cubed will be in the denominator when we consolidate. And then that x plus 10 is also going to go in the denominator. And so we can simplify this all in one step as the natural log of x minus 2 to the 7th over x cubed times x plus 10. Both of these expressions wind up in the denominator because of the subtraction here. If that went a little too fast for you, let me undo that. First, we would consolidate these by dividing the input, so we get the natural log of x minus 2 to the 7th over x cubed, and then we're subtracting the natural log of x plus 10. And now we divide these two expressions. So we get the natural log of x minus 2 over 7 divided by x cubed divided by x plus 10. But remember that dividing by an expression is the same as multiplying by its reciprocal. So instead of dividing by x plus 10, I'm going to multiply the top by 1 over x plus 10, and that's why the x plus 10 winds up in the denominator. A third way to do it would be to factor the -1 out of the last two terms and consolidate the expressions under addition. You can investigate that method as well. Let's end with a couple of examples that call back to ideas that we've talked about before. This first example says fill in the blank. The graph of y equals the common log of 100x is the graph of y equals the log of x shifted blank. And if that makes you a little bit confused, I don't blame you. This doesn't look like a shift at all. We learned earlier in the course that when you multiply the input by a number bigger than 1, that's a horizontal compression of the graph. What's the shift we're talking about here? Well, we can rewrite this logarithm using our new properties so that we can see what that shift is. Let's start with the common log of 100x. and rewrite it as the sum of two logarithms. This is the log of 100 plus the log of x. The common log of 100 is the exponent you have to put on 10 in order to get 100, and that's 2. So this is 2 plus log x, or maybe you'd feel more comfortable if I wrote it as the common log of x plus 2. When we rewrite it like this, now it's clear that this is a shift. We're adding 2 on the outside of the function, and so this shifts up 2 units. And because of modern technology, a trick like this doesn't seem super helpful. But I want you to think back to my day. When graphing calculators didn't exist, I couldn't possibly graph this function by thinking of this as a horizontal compression. How in the world am I going to compress this graph horizontally by a factor of 100? I have no chance of being able to draw that accurately. But if I use this property of logarithms and turn it into a shift by 2 units, well, I can shift the graph up 2 units. That's not going to be difficult. And it turns out that that's equivalent to compressing the graph horizontally by a factor of 100 in this example. Not in all examples, of course. But for this specific function, those two transformations are the same. It's going to be a lot easier to graph this by shifting up 2 units than trying to compress the graph horizontally by a factor of 100. Let's do another example like this, but here we would be stuck without the properties of logarithms because we don't have a transformation rule for something like this. This says the graph of y equals the natural log of the cube root of x is the graph of y equals the natural log of x compressed vertically by a factor of blank. We're going to fill in the blank. We have no rule for how to change a graph based on cube rooting the input. The effect of cube rooting the input would depend on the function that you've got. But with logarithms, we're in luck. We can rewrite this. Let me start with the original function, natural log of the cube root of x. Remember that that's the natural log of x to the 1/3. And now we can use that property of logarithms that allows us to pull out the exponent, and we get 1/3 times the natural log of x. And now you see why this is being described as a vertical compression, because we're multiplying by a number out front which is smaller than 1. When you multiply by a number between 0 and 1, that's a vertical compression of the graph, and it compresses it by a factor of 3. All of the y coordinates get multiplied by 1/3, but that's a compression by a factor of 3. Without this property of logarithms, it would have been difficult to see how to graph the natural log of the cube root of x. Now it's just a vertical compression. Getting these properties down takes practice, so I'd encourage you to dig up some practice problems. Do some textbook problems that ask you to expand expressions and to consolidate expressions. Dig up a couple examples of these graphing applications just so you can see a use for these things. And we'll continue next time with some equations. If you have any questions about the examples in this video, please reach out. You can see me in an office hour or you can send me emails.